continuation of what we previously discussed. So we talked about the plasma enhanced CVD for preparation of diamond, or plasma enhanced PVD for that matter. Okay. So in both cases, what we were doing, we were using either radio frequency, or we were using some sort of electrical forces to generate your plasma, arc discharge or something like that. But what we can also do is we can simply increase the temperature. And that is how we obtain our plasma. So this is also in a way a plasma enhanced CVD, but here the reactive hydrogen species that you're getting, and also some argon gas or whatever is your carrier gas, that is also getting ionized, but all of this is happening because of very high temperature. So for the hydrogen species, you know already that you need to go above 2000 degrees centigrade for getting the atomic hydrogen. So definitely this method requires above 2000 degrees centigrade temperatures. So if you want to go to such high temperatures, what you need is some sort of metal which can be joule heated. So number one, the metal should be able to withstand those temperatures, of metal or alloy. Also, the filament method works better because filaments are easier to heat using joule heating. Okay, so what you call this thermal CVD method is the hot filament method. Okay, so this filament or fiber or wire, that is made of tungsten in most cases, or some alloys such as tantalum. Okay, so these alloys then, or metal, then this is heated in up to above 2000 degrees centigrade. The one important thing is that this should take place very close to your substrate, because otherwise there will be very strong temperature gradient. So your wire is heated and you have plasma very close to the wire. But if your substrate is too far, by that time your plasma concentration will drastically decrease. Also because the thermal gradient, there is a very strong thermal gradient. So typically you'll have less than 1 centimeter distance between your substrate and the heated filament. Okay. Now again, you will use a mixture of methane. So this is in the case of CVD, you will use a mixture of methane, hydrogen, and also in this particular case, you will typically also use some oxygen. That helps in the formation of oxygen plasma. Okay, so you will use this combination as your feed gas. Okay. Now, in this particular case, one more thing that influences the deposition rate. So other things, the substrate temperature and the plasma intensity, all of these things are important. There's one more thing that is important, which is the distance between your hot filament and your substrate. Okay, so this is also you need to optimize. And that will also depend depending upon the size of the substrate, also you may have to change or also rotate your substrate. So all of these things then you need to sort of optimize. Okay, substrate in general may require cooling. So yeah, one interesting thing now is that you have very high temperatures very close to the substrate. So you have about 2000 degrees very close to the substrate, but your substrate should not be above 1000 degrees, that otherwise your diamond films may then again convert back to graphite. So in that case, what you're going to need is some sort of water cooling or any other cooling system for cooling your substrate separately in order to maintain its temperature below 1000 degrees. Okay. Although this is a simple method compared to arc discharge and so on, it is in general it should be also relatively inexpensive. But there is one disadvantage. The fact is that the lifetime of your wire is not very long. Still, it's like 500-600 hours, but still you may need to change your filament after that. So this is one disadvantage, the primary disadvantage of this process. Okay. There are some other methods also. So now we have discussed plasma enhanced PVD, plasma enhanced CVD method. There are some other methods which are known as flame or combustion methods. Okay, there you will use acetylene directly in the presence of oxygen, but again very high temperatures are required. So I'm not going into the details of this particular process because also it's very it's less common. Okay. So yeah, here basically you're going to use a brazing or welding torch, like torch. If you performed welding, then and that is where you're going to get your temperatures above 2000 degrees, and you have this oxyacetylene torch. Okay, fine. So what are the substrates? As I already mentioned, that substrates do not need anything too special, so they are not performing the role of catalyst in this particular case. So the most common substrate actually for these films is silicon, but often diamond films we require coating of these diamond films on different, for example, parts, automobile parts or other parts. So you can even use the entire part as your substrate. Okay. You can also use various refractory materials, and so graphite itself can be used in that case. Various carbides can be used, and other metals, alloys. As such, we are not too particular about the substrate when it comes to diamond CVD. Okay, so now coming to what is known as diamond-like carbon. So I mentioned in the beginning that vapor deposited diamond and diamond-like carbon, they are not the same. Okay, so actually again, around 1971 or so, people started using so this diamond-like carbon was accidentally produced at the time of when people were trying to produce vapor deposited diamond. Basically, this is nothing but a a type of carbon which has sufficiently high amount of sp3 carbon, but also a reasonable fraction of sp2 type carbon. So this is sort of a mixture of graphite and diamond. Even sometimes people show this kind of material on the phase diagram of carbon, because this is even though you have nanoscale crystals, you're always looking at the material as a bulk material, as coating material, and this is a material which is a very good which is something between diamond and graphite. So you have at the nanoscale, you have both diamond and graphite crystallites, and as a result, overall this material behaves like like an amorphous material. So physically this is an amorphous material. So in principle, by definition, okay, number one, this is a metastable form of diamond, so carbon, so it is something between diamond and graphite. Okay, and this is produced pretty much always by vapor deposition. So this is not a natural material. This is always produced artificially. Okay, and it is always produced in the form of thin film. Even the film thickness is not very high. Even in the case of vapor deposited diamond, you can get much thicker films compared to diamond like carbon film. And the idea is that you can have, in terms of composition, up to 50% graphite crystallites. So graphite and diamond nanocrystallites, very uniformly, so to say, distributed. But you also have hydrogen impurities. So you can think about it when somebody is trying to produce vapor deposited diamond and the purity is low. That initially was thought that this is this is just a bad or low purity diamond film, but then people realized that this film directly can be used for a lot of applications. In fact, this film has properties very similar to vapor deposited diamond films. So this can actually be a very good substitute, and in fact that is nowadays diamond like carbon coatings are more common than the vapor deposited diamond coatings, because they very much serve the purpose of providing the wear resistance, and the thermal optical properties are also very interesting for diamond like films. Okay, but again, diamond like carbon is not just one type of material. So again, depending upon the fraction of sp2 and sp2 carbon and hydrogen, you can further divide this material into different classes or subclasses and so on, subcategories. Okay, so importantly, diamond-like carbon is pretty much always called an amorphous form of carbon, because again, it depends on what is the scale at which we are talking. So we talked about also other types of carbon materials, non-graphitizing carbon, for example, glass-like carbon. Physically, yes, it shatters on breaking, and that is why you call it an amorphous material, but it is electrically conductive. So should you call it amorphous or not is a question. Also, that is the case with diamond-like carbon films, because you have both diamond and graphite type crystallites at the nanoscale. So you only have short range order. You pretty much never have long range order in the case of diamond like carbon, but at the nanoscale you do have crystallites present. However, one more thing which is different compared to non-graphitizing carbons here. Here the diamond-like carbon films are typically, their electrical and thermal properties also vary a lot, because you see you have an insulator and conductor mixed together, and then there are different fractions. And it is a polycrystalline type of film, so you cannot really say that these are the exact properties of this material. So that is why also in terms of properties, you can never say that this is electrically conductive or not, and depending upon the fraction of sp2 type carbon, it will change. So generally these films are called amorphous carbon films. So in fact, if you want to, often if you say, if you do an internet search, an example of amorphous carbon, then often you will hear diamond-like carbon. Okay, but you should understand that at nanoscale, we do have short range order in this material as well. Okay, fine. So yeah, as I said that this is not a natural material, the mechanical and thermal properties of this material are very similar to the vapor deposited diamond, and that is why we use this for a lot of technological applications. Okay, what you have as such in DLC, you have sp2 sp3 hydrogen as well as sometimes sp hybridized carbon. So this is basically a mixture of all types of carbons, but you do have a reasonable amount of sp3 carbon present, unlike other, so you will have in the case of disordered carbons or sometimes carbon fibers, you have sp2 hybridized carbon with some what you call amorphous regions. There you may have sp hybridized carbon, or even individual atoms might even be sp3 hybridized, but there is no well-defined order in those regions, and that is why the region is called amorphous. And then you have crystalline region. Altogether your material is known as the disordered carbon material. But in the case of DLCs, you can also have sp2 3 and sp and hydrogen, all of these things together, and that is why it's very difficult to get any long range order in this particular case. Okay, so I was saying that you can further divide DLCs. So there are two categories in which the diamond-like carbon is further classified. Number one is what is known as amorphous DLC, which, so you will often see this kind of A and then colon and then C. So this is used typically for DLC films, AC. These are your amorphous DLC films, and the second type is hydrogenated. So you know that hydrogen is present in all cases in DLC, but it depends upon what is the fraction of it. So it can be the atomic fraction of hydrogen can be between 1% up to 50%. So depending upon what is the fraction of your hydrogen, then you call it either hydrogenated or not, just amorphous DLC or hydrogenated DLC, sometimes also called amorphous hydrogenated DLC. So you write it like this, ACH. Okay, so let us talk about the amorphous DLC first. Okay, here you have a high content of sp3 carbon and less than 1% hydrogen. What else? You will generally produce it by a sputtering type of methods, generally using PVD. Okay, one more thing is that in the case of you still need plasma for the DLC production, but the temperatures can be slightly lower compared to what you need for vapor deposited, because there the continuous presence of hydrogen species was very important. And also the continuous activation of your carbon species. Here also it is important, but since you can live with slightly lower purities, purity in terms of sp3 fraction, so here you can have slightly lower temperatures compared to what you had for vapor deposited diamonds. Okay, so typically you will use for this kind of carbon you will use PVD or removing carbon from a graphite source. Okay. In the case of hydrogenated DLC fabrication, what you have is very high content, up to 50% of sp2 type carbon and also up to 50% of atomic fraction of hydrogen. So the point is that you can have a relatively much less fraction of your sp3 type carbon. Okay. In fact, sometimes there is so much hydrogen in the material that people call it a hydrocarbon, rather than considering it, a form of carbon. Okay. Yeah, and some sp hybridized carbon, as I mentioned, can also be present. So here in this diagram, you can see this is the hydrogen fraction, so 0.1, 0.2, and so on. And then you have the sp3 to sp2 ratio that is on your y-axis, and you can see how it increases. So there is a balance between this sp3 sp2 ratio and the fraction of hydrogen in the case of amorphous hydrogenated DLC. Okay, so now coming to the applications. So the applications here I have mentioned are for both DLC and vapor deposited diamonds, and these are just some representative applications. Of course, you can find also some other applications. The most interesting property of these materials, because these are coatings, these are films predominantly. So for these films, they provide friction resistance, so wear resistance to a lot of, so on a lot of tools, and especially in the case of high temperature applications where you require, the tool, you want to protect your tool or any part from wear, then in that case you use these DLC coatings, or vapor deposited diamond coating. Okay, so cutting and drilling tool, that is the most common application. You also have it for circuit board drills, or even the platforms that are used for sharpening your tool. So these are whetstones. So these are used for sharpening the tools. Also, there you can have DLC coatings. Okay. You actually have these kind of coatings also on various surgical tools, because these are also chemically very inert coatings. So whenever you need an inert coating on, and you want to protect your tool from thermal as well as mechanical wear, in that case you can use vapor deposited diamond or DLC. Okay, so again, on various bearings, even jet nozzles and extrusion dies, all of these parts wherever you want wear protection. You can also use these coatings for corrosion protection, for example, in the case of batteries, especially sodium batteries, and various, you can use lining in reaction vessels. You can use these coatings as lining on crucibles and so on. So for protecting it from corrosion and diffusion and so on. So okay, so diffusion barrier also this can make. Some other applications include the radiation detected photonic devices. So they have a photonic device application, very interesting optical properties, and therefore they can be used as coatings on lenses, and even used for they can be used for laser protection. Heat sink is also an important application because of good thermal conductivity of these films. So they can be used as heat sink also in a lot of electronic devices, also in your circuit board and computers. They are used a lot, and various different types of sensors can be produced using diamond-like carbon. Okay, and field effect transistors. So a lot of electronic and sensor device applications. You actually have a lot of scattered publications where DLC and vapor deposited diamond has been used for all of these applications. Okay, so yeah, same thing. These are also applications, as I mentioned, for both DLC and vapor deposited diamond. So here I have provided some resources for further reading. In addition to that, of course, you can find various other review articles that are related to these types of diamond films.